Hello everyone! We are starting a free open lecture on our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the lecture times, join our Telegram channel and look for the schedule. Well, we will start with the very worst. Here they are marked in red, yellow, and green colors. Here on the green ones, the root graph or sublinear is not drawn. But in principle, it is very similar to the logarithmic one. That is, it is like a curve 2 to the power, only it goes to the right. That's the kind of curvature it has. Accordingly, we have the most complex algorithm, or rather, the most complex complexity, if you can say so, O of n. It is also called factorial. That is, it is clear that the larger our O, the more multiplications we have. So, if we remember what a factorial is, it is 1 multiplied by 2, multiplied by 3, multiplied by 4, multiplied by 5, and so on and so forth. The larger our n, the more elements we have in the product, which sequentially increase by 1. Thus, it increases too much, that is beyond exponentiality, so we have such a graph. Well, it will only work for small numbers. Yes, I doubt that anyone will use it, say, when n equals, say, 1,000, for example. That is, the complexity will grow unrealistically, and it will be very difficult to calculate. Well, you either need an extremely powerful machine, or you will have to wait a very long time to get the solution. The next complexity we have is O2, which is also called exponential, because there is an exponent, which is ex, and here instead of ex, it is 2. That is, they are similar in terms of structure, but e is approximately 2 and 7 something, while here it is just 2. Therefore, the graphs look very similar, but that graph will be cooler, and indeed it will be cooler, and indeed it will be cooler. From the point of view of the slope, that is, it starts to grow faster, which is why they are very similar and are called exponential. But this graph will not be as steep in terms of slope, you could say, or in terms of growth potential, so you could call it that. Accordingly, next we have the following complexity, and here is the graph of 2 to the power of n, which means it works faster than n, but still not as fast as we would like. The next complexity we have is ON2, also called quadratic complexity, but this one is simple, kind of. Squared, therefore square, meaning it's very simple here. Most often such an algorithm is some kind of brute force, that is, a complete search, which corresponds to it. Accordingly, the next complexity we have is n multiplied by the logarithm of n to the base 2, which is linear logarithmic. Why is it linear logarithmic? It's simple, O of n is linear, and logarithm is logarithmic, so n multiplied by log is linear logarithmic, so it's very simple here. It already operates with such a bad, but not extremely bad, complexity, and of course it works faster, so they go from the slowest to the fastest. This kind of graph is acceptable.
Want to become a great programmer? Subscribe to our Telegram channel.
What operates with this complexity? Some quick sort, for example, it operates with n logarithm. Next comes linear complexity. Quick sort suits me well. Then comes linear complexity next, meaning it is already working in a reasonably acceptable time. For some computational algorithms, all this will work. For example, a traversal of an array where we find the largest possible element in the array, or we traverse through the entire array and find out the count of certain elements within a map. That is to say, we have some remainders from dividing any given number, for instance, by 2, and everything gets divided with either a remainder of 0 or 1. This helps us calculate everything efficiently using linear complexity. That is, we go through some data array once, or through some lines of data, or something else through some line, that is, something that has a line, and thus we fill in some other data, or we may not fill it in. In general, the traversal itself already takes O10. The next complexity we have is sublinear complexity, or the square root of n from the square root of n. So, what operates with such complexity? Well, there is all sorts of square root tree, which is something like the square root of n times something. Or for example, we can find the divisors of a number. That is, to find all the divisors of a number, for instance, it is required to take the complexity of root and zen, because there is a comparison before the root and after the root. For example, if the divisor is up to the root, such as some unit, it corresponds to the second number, which is found by dividing this number by the unit, that is the number itself. If a number is divisible by 2, it obviously has a pair, because the product comes from two numbers to get some third number. Accordingly, this algorithm will work with root complexity. Accordingly, with logarithm complexity. What do we have for logarithm? Binary search operates with logarithmic complexity. If the array is already sorted in advance, meaning we do not use any sorting for n log, so that the total complexity becomes n logarithm, that is, binary search works in logarithm time. And lastly, there is constant complexity. This is when we are given a formula and we can immediately calculate the formula, meaning we do not go through any cells, or for example, a simple operation like adding a unit. That is, adding a unit is a complexity that simply means we have +1. Yes, somewhat. Most often, it shows that we have no dependency on any n, that is, it is determined by some unit. But again, we have an example of constant complexity. We have some function f, and in it, for example, there is a loop over 100 elements.
Want to become a great programmer? Subscribe to our Telegram channel.